Chapter 14, the Document Object Model. Too bad, same old story. Once you've finished building your house, you notice you've accidentally learned something that you really should have known before you started. Friedrich Nietzsche, Beyond Good and Evil. When you open a web page, your browser retrieves the page's HTML text and parses it, much like our parser from Chapter 12 parse programs. The browser builds up a model of the document structure and uses this model to draw the page on the screen. This representation of the document is one of the toys that a JavaScript program has available in its sandbox. It is a data structure that you can read or modify. It acts as a live data structure. When it's modified, the page on the screen is updated to reflect the changes. Document structure. You can imagine an HTML document as a nested set of boxes. Tags such as body and body enclose other tags, while in turn contain other tags or text. Here's the example document from the previous chapter. This page has the following structure. The data structure the browser uses to represent the document follows this shape. For each box, there's an object which we can interact with to find out such things as what HTML tag it represents and which boxes or text it contains. This representation is called the Document Object Model, or DOM for short. The global binding document gives us access to these objects. Its document element property refers to the object represented in an HTML tag. Since every HTML document has a head and a body, it also has a head and a body properties pointing to those elements. Trees. Think back to the syntax trees from Chapter 12 for a moment. Their structures are strikingly similar to the structure of a browser's document. Each node may refer to other nodes' children, which in turn have their own children. This shape is typical of nested structures, where elements can contain sub-elements that are similar to themselves. We call a data structure a tree when it has branching structure, no cycles, a node may not contain itself directly or indirectly, and a single well-defined root. In the case of the DOM, document.documentElement serves as the root. Trees come up a lot in computer science. In addition to representing recursive structures such as HTML documents or programs, they're often used to maintain sorted sets of data because elements can usually be found or inserted more efficiently in a tree than in a flat array. A typical tree has different kinds of nodes. The syntax tree for the egg language has identifiers, values, and application nodes. Application nodes may have children, whereas identifiers and values are leaves or nodes without children. The same goes for the DOM. Nodes for elements which represent HTML tags determine the structure of the document. These can have child nodes. An example of such a node is document.body. Some of these children can be leaf nodes such as pieces of text or comment nodes. Each DOM node has a node type property which contains a code number that identifies the type of node. Elements have code 1, which is also defined as the constant property node.elementNode. Text nodes represent a section of text in the document, get code 3, node.textNode. Comments have code 8, node.commentNode. Another way to visualize our document tree is as follows. The leaves are text nodes, and the arrows indicate parent-child relationships between nodes. The standard. Using cryptic numeric codes to represent node types is not a very JavaScript-like thing to do. Later in this chapter, we'll see that other parts of the DOM interface also feel cumbersome and alien. This is because the DOM interface wasn't designed for JavaScript alone. Rather, it tries to be a language-neutral interface that can be used in other systems as well, not just for HTML, but also for XML, which is a generic data format with an HTML-like syntax. This is unfortunate. Standards are often useful, but in this case, the advantage, cross-language consistency, isn't all that compelling. Having an interface that is properly integrated with the language you're using will save you more time than having a familiar interface across languages. As an example of this poor integration, consider the child nodes property that element nodes in the DOM have. This property holds an array-like object with a length property and properties labeled by numbers to access the child nodes. But it is an instance of the node list type, not a real array, so it does not have methods such as slice and map. Then there are issues that are simply caused by poor design. For example, there's no way to create a new node and immediately add children or attributes to it. Instead, you have to first create it and then add the children and attributes one by one using side effects. Code that interacts heavily with the DOM tends to get long, repetitive, and ugly. But these flaws aren't fatal. Since JavaScript allows us to create our own abstractions, it's possible to design improved ways to express the operations we are performing. Many libraries intended for browser programming come with such tools. Moving through the tree. DOM nodes contain a wealth of links to other nearby nodes. The following diagram illustrates these. Although the diagram shows only one link of each type, Every node has a parent node property that points to the node it is part of, if any. Likewise, every element node, node type 1, has child nodes property that points to an array-like object holding its children. In theory, you could move anywhere in the tree using just these parent and child links, but JavaScript also gives you access to a number of additional convenient links. The first child and last child properties point to the first and last child elements, or have the value null for nodes without children. Similarly, previous sibling and next sibling points to adjacent nodes, which are nodes of the same parent that appear immediately before or after the node itself. For a first child, previous sibling will be null, and for a last child, next sibling will be null. There's also the children property, which is like the child nodes, but contains only element type 1 children, not other types of child nodes. This can be useful when you aren't interested in text nodes. When dealing with a nested data structure like this one, recursive functions are often useful. The following function scans a document for text nodes containing a given string and returns true when it has found one. The node value property of a text node holds the string of text that it represents. Finding elements. Navigating these links among parents, children, and siblings is often useful. But if we want to find a specific node in the document, reaching it by starting at document.body and following a fixed path of properties is a bad idea. Doing so bakes assumptions into our program about the precise structure of the document, the structure you might want to change later. Another complicating factor is that the text nodes are created even for the white space between nodes. The example document's body tag has not just 3 children h1 and 2p elements, but 7, those 3 plus the spaces before, after, and between them. If we want to get the href attribute of the link of that document, we don't want to say something like get the second child of the sixth child of the document body. It would be better if we could say get the first link in the document, and we can. All element nodes have a getElementByTagName method, which collects all elements with the given tag name that are descendants, direct or indirect children, of that node and returns them as an array-like object. To find a specific single node, you can give it an ID attribute and use document.getElementById instead. A third similar method is getElementsByClassName, which is like getElementsByTagName, searches through the contents of an elements node and retrieves all elements that have a given string in their class attribute. Changing the document. Almost everything about the DOM data structure can be changed. The shape of the document tree can be modified by changing parent-child relationships. Nodes have a remove method to remove them from their current parent node. To add a child node to an element node, we can use the append child, which puts it at the end of a list of children, or insert before, which inserts the node given as the first argument before the node given as the second argument. A node can exist in the document in only one place. Thus, inserting paragraph 3 in front of paragraph 1 will first remove it from the end of the document and then insert it at the front, resulting in 3, 1, 2. All operations that insert a node somewhere will, as a side effect, cause it to be removed from its current position if it has one. The replaceChild method is used to replace a child node with another one. It takes as arguments 2 nodes, a new node and the node to be replaced. The replaced node must be a child of the element the method is called on. Note that both replaceChild and insertBefore expect the new node as their first argument. Creating nodes. Say we want to write a script that replaces all images, image tags, in the document with their text held by their alt attributes, which specifies an alternative textual representation of the image. This involves not only removing the images, but also adding a new text node to replace them. Given a string, createTextNode gives us a text node that we can insert into the document to make it show up on the screen. The loop that goes over the images starts at the end of the list. This is necessary because the node list returned by a method like getElementByTagName or a property like childNodes is live. That is, it's updated as the document changes. If we started from the front, removing the first image would cause the list to lose its first element, so the second time the loop repeats, where I is 1, it would stop because the length of the collection is now also 1. If you want a solid collection of nodes as opposed to a live one, you can convert the collection to a real array by calling array.from. To create element nodes, you can use a document.createElement method. This method takes a tag name and returns a new empty node of the given type. The following example defines the utility elt, which creates an element node and treats the rest of its arguments as children to that node. This function is then used to add an attribution to a quote. Attributes. Some element attributes, such as href for links, can be accessed through a property of the same name of the element's DOM object. This is the case for most commonly used standard attributes. HTML allows you to set any attribute you want on nodes. This can be useful because it allows you to store extra information in a document. To read or change custom attributes, which aren't available as regular object properties, you have to use the getAttribute and setAttribute methods. It is recommended to prefix the names of such made-up attributes with data to ensure that they do not conflict with other attributes. There is a commonly used attribute, class, which is a keyword in the JavaScript language. For historical reasons, some old JavaScript implementations could not handle property names that match keywords. The property used to access this attribute is called class name. You can also access it under its real name class with the getAttribute and setAttribute methods. Layout. You may have noticed that different types of elements are laid out differently. Some such paragraphs P or headings H1 take up the whole width of the document and are rendered on separate lines. These are called block elements. Others, such as links A or the strong element, are rendered on the same line with their surrounding text. Such elements are called inline elements. For any given document, browsers are able to compute a layout which gives each element a size and a position based on its type and content. This layout is then used to actually draw the document. The size and position of an element can be accessed from JavaScript. The offset width and offset height properties gives you the space that the element takes up in pixels. A pixel is a basic unit of measurement in the browser. It traditionally corresponds to the smallest dot that the screen can draw, but on modern displays which can draw very small dots, that may no longer be the case, and the browser pixel may span multiple display dots. Similarly, client width and client height give you the size of the space inside the element, ignoring border width. The most effective way to find the precise position of an element on the screen is the getBoundingClientRect method. It returns an object with the top, bottom, left, and right properties, indicating the pixel position of the side and the element relative to the upper left of the screen. If you want pixel positions relative to the whole document, you must add the current scroll positions, which you can find in the page X offset and page Y offset bindings. Laying out a document can be quite a lot of work. In the interest of speed, browser engines do not immediately relay out a document every time you change it, but wait as long as they can before doing so. When a JavaScript program that changed the document finishes running, the browser will have to compute a new layout to draw the changed document to the screen. When a program asks for the position or size of something by reading properties such as offset height or calling getBoundingClientRect, providing that information also requires computing a layout. A program that repeatedly alternates between reading DOM layout information and changing the DOM forces a lot of layout computations to happen and will consequently run very slowly. The following code is an example of this. It contains two different programs that build a line of X characters 2,000 pixels wide and measures the time each one takes. Styling. We have seen that different HTML elements are drawn differently. Some are displayed as blocks, others inline, some add styling, strong makes its content bold, and A makes it blue and underlines it. The way an image tag shows an image or an A tag causes a link to be followed when it is clicked is strongly tied to the element type. But we can change the styling associated with an element, such as a text color or underline. Here's an example that uses the style property. A style attribute may contain one or more declarations, which are properties such as color followed by a colon and a value such as green. When there is more than one declaration, they must be separated by semicolons, as in color red, border none. A lot of aspects of the document can be influenced by styling. For example, the display property controls whether an element is displayed as a block or an inline element. The block tag will end up on a line of its own, since block elements are not displayed in line with the text around them. The last tag is not displayed at all. Display none prevents an element from showing up on the screen. This is a way to hide elements. It is often preferable removing them from the document entirely because it makes it easy to reveal them again later. JavaScript code can directly manipulate the style of an element through the element style property. This property holds an object that has properties for all possible style properties. The values of these properties are strings, which we can write to in order to change a particular aspect of the element's style. Some style property names contain hyphens, such as font family. Because such property names are awkward to work with in JavaScript, you'd have to say style font family. The property name and the style object for such properties have their hyphens removed and the letters after them capitalized, style.fontFamily. Cascading styles. The styling system for HTML is called CSS for cascading style sheets. A style sheet is a set of rules for how to style elements in a document. It can be given inside a style tag. The cascading in the name refers to the fact that multiple such rules are combined to produce the final style for an element. In the example, the default styling for strong tags, which gives them the font weight bold, is overlaid by the rule in the style tag, which adds font style and color. When multiple rules define a value for the same property, the most recent rule gets a higher precedence and wins. For example, if the rule in the style tag included font weight normal, contradicting the style font weight rule, the text would be normal, not bold. Styles in a style attribute applied directly to the node have the highest precedence and always win. It's possible to target things other than tag names and CSS rules. A rule for .abc applies to all elements with ABC in their class attribute. A rule for hashtag XYZ applies to the element with the ID attribute of XYZ, which should be unique within the document. The precedence rule favoring the most recently defined rule applies only when the rules have the same specificity. A rule's specificity is a measure of how precisely it describes matching elements, determined by the number and kind, tag, class, or ID of element aspects it requires. For example, a rule that targets p.a is more specific than a rule that just targets p or just .a and would thus take precedence over them. The notation p greater than a applies the given style to all a tags that are direct children of p tags. Similarly, p space a applies to all a tags inside p tags, whether they are direct or indirect children. Query selectors. We won't be using style sheets very much in this book. Understanding them is helpful when programming in the browser, but they are complicated enough to warrant a separate book. The main reason I introduced selector syntax, the notation used in style sheets to determine which elements a set of styles apply to, is that we can use the same mini-language as an effective way to find DOM elements. The query selector all method, which is defined both on the document object and on element nodes, takes a selector string and returns a node list containing all the elements that it matches. Unlike methods such as getElements by tag name, the object returns by query selector all is not live. It won't change when you change the document. It is still not a real array though, so you need to call array.from if you want to treat it like one. The query selector method without all part works in a similar way. This one is useful if you want a specific single element. It will return only the first matching element or null if no element matches. Positioning and animating. The position style property influences layout in a powerful way. It has a default value of static, meaning the element sits in its normal place in the document. When it is set to relative, the element still takes up space in the document, but now the top and left style properties can be used to move it relative to that normal place. When position is set to absolute, the element is removed from the normal document flow. That is, it no longer takes up space and may overlap with other elements. Its top and left properties can be used to absolutely position it relative to the upper left corner of the nearest enclosing element, whose position property isn't static, or relative to the document if no such enclosing elements exist. We can use this to create an animation. The following document displays a picture of a cat that moves around in an ellipse. Our picture is centered on the page and given a position of relative. We'll repeatedly update that picture's top and left styles to move it. The script uses a request animation frame to schedule the animate function to run whenever the browser is ready to repaint the screen. The animate function itself again calls request animation frame to schedule the next update. When the browser window or tab is active, this will cause updates to happen at a rate of about 60 per second, which tends to produce a good-looking animation. If we just updated the DOM in a loop, the page would freeze and nothing would show up on the screen. Browsers do not update to their display while a JavaScript program is running, nor do they allow any interaction with the page. This is why we need request animation frame. It lets the browser know that we are done for now, and it can go ahead and do the things that browsers do, such as updating the screen and responding to user actions. The animation function is passed the current time as an argument. To ensure that the motion of the cat per millisecond is stable, it bases the speed at which the angle changes on the difference between the current time and the last time the function ran. If it just moved the angle by a fixed amount per step, the motion would stutter when, for example, another heavy task running on the same computer prevented the function from running for a fraction of a second. Moving in circles is done using the trigonometry function math.cos and math.sin. For those who aren't familiar with these, I'll briefly introduce them since we'll occasionally use them in this book. Math.cos and math.sin are useful for finding points that lie on a circle around point 0, with radius of 1. Both functions interpret their argument as the position on this circle, with 0 denoting the point on the far right of the circle going clockwise until 2 pi, about 6.28, has taken us around the whole circle. Math.coast tells you the x-coordinate of the point that corresponds to the given position, and math.sign yields the y-coordinate. Positions or angles greater than 2 pi or less than 0 are valid. The rotation repeats so that alpha plus 2 pi refers to the same angle as alpha. This unit for measuring angles is called radians. A full circle is 2 pi radians, similar to how it's 360 degrees when measuring in degrees. The constant pi is available as math.pi in JavaScript. The cat animation code keeps a counter angle for the current angle of the animation and increments it every time the animate function is called. It can then use this angle to compute the current position of the image element. The top style is computed with math.sign and multiplied by 20, which is the vertical radius of our ellipse. The left style is based on math.cosine and multiplied by 200, so that the ellipse is much wider than its height. Note that styles usually need units. In this case, we have to append px to the number to tell the browser that we are counting in pixels as opposed to centimeters, ems, or other units. This is easy to forget. Using numbers without units will result in your style being ignored, unless the number is 0, which always means the same thing regardless of its unit. Summary. JavaScript programs may inspect and interfere with the document of the browser in displaying through data structure called the DOM. This data structure represents the browser's model of the document, and a JavaScript program can modify it to change the visible document. The DOM is organized like a tree, where elements are arranged hierarchically according to the structure of the document. The objects representing elements have properties such as parent node and child nodes, which can be used to navigate through this tree. The way a document is displayed can be influenced by styling, both by attaching styles to nodes directly and by defining rules that match certain nodes. There are many different style properties such as color or display. JavaScript code can manipulate an element's style directly through a style property. Exercises. Build a table. An HTML table is built with the following tag structure. For each row, the table tag contains a tr tag. Inside these tr tags, we can put cell elements, either heading cells th or regular cells td. Given a dataset of mountains, an array of objects with name, height, and place properties, generate the DOM structure for a table that enumerates the objects. It has one column per key and one row per object, plus a header row with th elements at the top listing the column names. Write this so that the columns are automatically derived from the objects by taking the property name of the first object in the data. Show the resulting table in the document by appending it to the element that has an ID attribute of mountains. Once you have this working, right-align cells that contain number values by setting their style.textAlign property to right. Elements by tag name. The document.getElementsByTagName method returns all child elements with a given tag name. Implementing your own version of this as a function that takes a node and a string, the tag name as arguments, and returns an array containing all descendant element nodes with the given tag name. Your function should go through the document itself. It may not use a method like querySelectorAll to do the work. To find the tag name of an element, use its node name property, but note that this will return the tag name in all uppercase. Use the toLowercase or toUppercase string methods to compensate for this. The cat's hat. Extend the cat animation defined earlier so that both the cat and his hat, image source image hat.png, orbit at opposite sides of the ellipse. Or make the hat circle around the cat, or alter the animation in some other interesting way. To make positioning multiple objects easier, you'll probably want to switch to absolute positioning. This means that top and left are counted relative to the upper left of the document. To avoid using negative coordinates, which would cause the image to move outside the visible page, you can add a fixed number of pixels to the position values.